Hi, my name is Jeff Butler, and I'd like to first thank you for taking the time to view our tutorial on how to choose an operating frequency for your wireless network. One of the first things we want to consider is do you have the opportunity to operate in a licensed or an unlicensed frequency band? If you can and you have that option, you'd want to choose a licensed or protected band if so permitted. These licensed bands are restricted, however, to authorized users, but they do provide relatively interference-free transmission and higher transmit power allowances than the unlicensed band. If we run through some of the bands that we offer in our product, we've got the 1.3 gigahertz or L band, which is for federal users, and that's the RM1370 series of product. The 1.6 gigahertz band, again for federal users. The 1.8 gigahertz band is also in that federal user space, and then 2.2 gigahertz or the S band. That's for Fed users and it's very typical in UAV or unmanned aerial vehicle deployments. We have the 4.0 to 5.0 gigahertz C band, it's known as. That's also federal users, and it's assigned to the Department of Justice, FBI, ATF, Department of Homeland Security, and those agencies, and it's the RM 4700 series of product we have that is in that frequency band of operation. A subset of that band is the 4.9 gigahertz public safety band, and that's basically state municipal public safety, police, fire, EMT, etc. can operate within that band, and that also falls within the RM 4700 product that we have. In terms of the unlicensed bands, these are public domain bands, and they are known also as the ISM bands for instrumentation, scientific, and medical equipment operation bands, and they're governed by the FCC Part 90 rules here in the U.S., and they're publicly shared spectrum, but they're a little lower power due to being unlicensed. The FCC regulates the power levels down a little bit as compared to the unlicensed bands, and also you have a higher potential for interference and congestion within those bands. And the three bands we'll talk about in the unlicensed band, or public domain, here are the 915 megahertz band, the 2.4 gigahertz band, and the 5.1 to 5.9 gigahertz band as well. There is an additional band, which is kind of a hybrid. Better we look at it, it's the CBRS band. That's the Citizens Broadband Radio Service band. It's unlicensed, but it is regulated. It's kind of a hybrid between a licensed and unlicensed bands. It's allowed for commercial use. Commercial use is authorized with a dynamically regulated spectrum authorization system, or SAS. What that means is you basically take your radio's location and the channel plan you prefer to operate under, and you register that with the SAS electronically, and then you will be then permitted to operate on those assigned channels once confirmed, and those channels will be protected for you going forward. So someone coming in after you will not be permitted to operate along those frequencies. So it gives you a very clear channel plan to operate under. The frequency of operation for this band is the 3.65 gigahertz band. That operates from 3550 to 3700 megahertz, and it operates in 15 10 megahertz wide channels. And it is limited, however, to terrestrial links. There's no allowance here by the FCC for ground-to-air communications, so UAVs are not permitted, but ground-to-ground links are. There is a minimal licensing fee to operate the SAS, and that's between $2 and $4 per month, and it's a good option in cases where that might be applicable to your particular topology. So to talk a little bit more, the one thing we always want to be conscious of is congestion and interference. If we're operating in unlicensed frequencies, this is really a concern that we want to be able to mitigate that, and we can. So the upper graph we show here is basically, it's a nearly wireless time domain spectrum. All of our signals operate in a certain time slot or time domain, T0 to T1, and we occupy time slots within that particular channel. So if we look at the first graph, we've got the available time slots here in black. These lines indicate the slots that are available for us to transmit over. And in the lower part of the graph, we see the utilized. The colored lines are the time slots that are being utilized by another operator. So in this particular example here, there are very few occupied or preoccupied time slots. It's a very open channel and would be ideal for us to operate in a band such as this particular scenario here on this particular frequency. If we look at the lower graph, this is a very highly congested, this is kind of the opposite end of the spectrum. It's a highly congested band where we have many fewer available time slots here for us to operate under, because as we see here, these different colored lines are different carriers or operators operating within our particular time domain on this particular channel, and our time slots are being utilized by these other interference sources. So they've already taken quite a few. And if you look at even more closely here, the thickness of the line indicates basically the size of the modulation rate, or the actual speed at which the channel is being occupied by the transmitter. A narrower line indicates a higher modulation rate or a faster talking signal. A thicker line here indicates a slower or lower modulation rate signal. This is common because there are different technologies that are deployed at different frequencies, and whether it be direct sequence spread spectrum, which operates much slower than today's operating signals, and these are out there. So the slower they talk, the more time slots they take, and it's a combination of this that will be part of your congestion. So what you'd want to do in the unlicensed spectrum in a case like this, you want to look at your channel and do some channel planning. You'd want to take and operate our spectrum analysis tool per se, and see what channels are free, what channels are clear, and operate in those less congested channels, and also at the same time operate on the smallest channel bandwidth as possible. Lower channel bandwidth that you operate under, the smaller it is, the less probability you have of getting hit with other interference. So those are things we can do definitely to mitigate a congested band and try to avoid channels like this that are more congested than others in the unlicensed band. Physics play a big role here as well. So how do we want to choose a higher or lower frequency? And again, waveform physics will tell us a lot of what we want to choose in terms of that. And if we look at our graphing here, the lower frequency signal here is basically 2 cycles. We see 2 waveforms in the same period of time, or 2 cycle or 2 hertz frequency. And the higher frequency signal is basically 4 waveforms, or 4 hertz of frequency here. Now, we can also look at not just frequency but wavelength. Both of these play a role in the physics of how waves propagate. The wavelength is basically a measurement of lambda. That's the distance between the same point of the wave, or a peak to a peak, or a trough to a trough, and that's the wavelength lambda. Frequency f and wavelength lambda, the formula and how they relate to each other is here, where lambda, or the wavelength, is equal to the velocity of the signal, or basically measured at the speed of light, divided by the frequency of signal. So if we look at how these two correlate to each other, the higher the frequency signal, such as this, has a shorter wavelength, and the larger the frequency and the smaller the frequency of signal, the larger the wavelength between the two. So lower frequency has a larger wavelength than a higher frequency signal. And this is important to understand because that'll tell us a lot about how these waves propagate and what our propagation environment is for our particular requirements. We can look at this, kind of graph this right out, and how it really plays out, and how the relative wavelengths are. So at 900 megahertz, the actual wavelength of one wavelength at 900 megahertz equals about 13.1 inches in length. If we increase the frequency to 2.4 gigahertz, the wavelength is 4.9 inches in length. We go even higher yet to 5.8, and the wavelength is 2 inches in length. So think of this in terms of physics. Look at this as electrical momentum, or the momentum of the wave going through the air. The larger the wavelength, the more momentum that signal has, and the more it will penetrate through or carry through free space as well as objects. The higher the frequency, the smaller the wavelength, the less electrical momentum that the signal has, the less it can carry itself through free space, and the less it will penetrate objects. So lower frequency, higher momentum for penetrating objects and getting through free space, higher frequency, smaller wavelength, and less opportunity to penetrate through the resistance of air, free space, and objects. So some advantages and disadvantages to both. So let's take a look at how these stack up. So the higher the frequency, the smaller the Fresnel zone requires. It means less clearance is required at higher frequencies, and we'll talk about that in some upcoming slides. Also, another advantage of higher frequency signals like 5.8 is potentially lower interference floor. What I mean by that is the interference sources that are out there, because they're operating at a high frequency as you are, they also have less propagation capability, and they will also therefore provide a smaller collision domain. So they have less chance of reaching you because they don't propagate as far either. But the disadvantages of it are there's a shorter propagation distance at this frequency for your carrier signal. So the higher the frequency, the shorter the range of the links. And also at the same time, the higher frequency, less penetration or higher attenuation you'll have of these higher frequency signals when encountering objects in your path. At lower frequencies, like 900 megahertz, you'll have far greater propagation distances, and you'll have much greater penetration of objects in the path at the lower frequencies. But the opposite is also true. The negatives are larger Fresnel zone clearance is required, bigger Fresnel zone at a lower frequency, and also you have a larger potential interference floor because your interference sources, the other transmitters out there in your territory, are going to have a higher probability of reaching you because their collision domains are larger, because at the lower frequencies they propagate further. So the interference propagates better. You propagate well, but so does the interference around you. So that's why you'll have to take this into account as you look at your particular area of coverage. Let's look at penetration in terms of non-line of sight. This is a typical case study we have of an example from one of our clients who did a UGV, or unmanned ground vehicle deployment, in a forested area, highly wooded forestry area, where you've got basically a 500-meter distance requirement from ground controller to the UGV itself, and the UGV was going to be bringing back 4K video along with telemetry. So they want to have at least a megabit, 2 megabits of data throughput to sustain their particular application requirements. So in this application, at 500 meters distance at 915 megahertz, pure non-line of sight with the tree obstruction, we sustained in this case 2 to 3 megahertz of throughput throughout this half a kilometer distance through trees. So this was more than adequate to meet their requirements for high definition video. Had they attempted this or tested this at 2.4 gigahertz or 5 gigahertz, it would have been a no-go. You wouldn't have a link at those frequencies because this would provide too much of an obstruction at those higher frequencies. But at 900 megahertz in the unlicensed band, or at 1.3 gigahertz in the licensed frequency space, this link is very feasible and works well. If we look at a different application, more of a UAV application for an aerial vehicle, we want to look at 2.4 gigahertz or 915 megahertz. Let's compare the two. So our case study here is a 5-kilometer link. We have a hovering height of 55 meters for our UAV, and then in the path again we have some trees, and they're about 10 meters in height. So we're going to have to take this into consideration as we look at our point-to-point link here at the different frequencies, 2, 4, and 900, and what does a Fresnel zone look like, and how will this path play out when we run it through our calculation tool. So let's take a look and see which of these two paths, based on device wave physics, will actually work better. So first, we take a look at 915 megahertz. So if we look at first from a Fresnel zone clearance, let's also look at what's the propagation look like, and what kind of a link receive level from a link RSSI. What kind of receive level are we going to have at 915 megahertz at 5 kilometers? So in this case, with clear RF line of sight, our projected receive level, or RSSI, from transmit to receiver is a minus 71 dBm. That's an excellent signal level. It'll allow us to operate on a clear line of sight. Will allow us to operate at some of the higher modulation rates. So that would be ideal. The challenge is, if we look at the physics of it, what the Fresnel zone looks like, it's not a good picture. So if we come over here and look at the 0.6 F1 boundary, which is this green dotted parabola here, this area has to be free of obstruction. The 0.6 Fresnel zone has to be free of obstruction for us to have a solid and stable link, which we would anticipate here, which we're looking to replicate here. The challenge we have is, with the tree line obstruction we've got at 10 meter height, it absorbs a good portion of our Fresnel zone, the 6/10 Fresnel zone, and we also have an impingement point here caused by the ground at this frequency as well, at 915 megahertz. Just the shape of the Fresnel zone, the size of it, is going to be a no-go when it comes to this particular path with these particular obstructions at this link distance. So 900 is not going to work favorably. As we raise our frequency bar to 2.4 gigahertz, let's take a look and see how that would operate and what we have there. So when we look at 2.4, although it has a lower RSSI anticipated receive level of minus 80, remember our previous 915 megahertz signal was minus 71. 2.4 gigahertz, again, doesn't propagate as well through free space, so it's a minus 80. So you lose about 9 dB of propagation over these 5 kilometers, but that's still more than enough receive level to operate in the low to middle modulation rates of our radio, which is fine for this application. We'll sustain good throughput there. How does it look from a Fresnel zone standpoint? If we look here, it's much cleaner. So because it operates at a narrower Fresnel zone at 2.4, we have no impingement caused by the tree line whatsoever, and the ground is also not a problem. So although a slightly less compromise in terms of receive level, still within our operating range for a good link, and our Fresnel zone's clean and green. So the higher frequency allows us, it buys us that added Fresnel zone advantage, which we need for this particular UAV deployment. And in conclusion, how do we mitigate? The key is mitigating. One of the things we have to do is mitigating potential interference. So if you can choose a licensed or protected band, we're authorized to do so. If we want to look at the unlicensed bands, kind of stacking them up a little bit here, 2.4 gigahertz is typically less congested in rural areas, but more congested in urban areas where you have other Wi-Fi users. At 2.4, you also have microwave ovens and things of that nature in the urban areas, so it's got a bit more congestion there just typically. 915 megahertz band is more congested, believe it or not, in outlying areas due to municipal networks that are already in existence for SCADA, water, wastewater management, that type of thing. Those networks have been out there for a while. They're up on towers, high towers, and they're broadcasting longer distances because 900 propagates further. So the collision domain in the outlying areas seems to be more of a problem for 900 with typically more congestion there versus in the urban areas. 5 gigahertz of all the bands in the unlicensed spectrum is the least susceptible to interference. The smallest collision domain, very favorable from an interference floor standpoint, but the range, and again, the absorption of free space is higher, so your range is less at 5 gigahertz, and obstructions are much more of a limiting factor to the higher frequency, smaller wavelength here in the 5 gigahertz band. So those are the negatives. Less interference, but more obstruction due to range and obstructions in the path. And in terms of your particular topology, we want to look at terrain and obstruction, and what does your topology look like? You have to evaluate it from that perspective, what you're trying to face, whether it's trees, etc. And at short ranges, as we showed, the lower frequencies like 900 megahertz for unlicensed or 1.3 gigahertz for licensed will be very effective in mitigating effects such as trees and building walls, etc. So UGV application, lower frequency is typically your way to go. Increasing the frequency will shrink the Fresnel zone. So for requirements for UAVs and that we're trying to get clearance over objects, then the higher frequency signal offers a much better solution. 2.4 gigahertz or 2.2 for the licensed bands or higher is better there. And for your particular application, if there are questions you have, we'd be more than happy to address those directly with you and your specifics. So please contact us at sales@doodlelabs.com. I want to thank you again for taking the time and look forward to working with you in the future.